Today, Elizabeth is going to talk about explainable AI for climate science, opening the black box to reveal planet Earth. And with that, welcome, Professor Barnes, and we very much look forward to your presentation. And thank you again for accepting our invitation, and thanks to all of you for attending. If you have questions, don't hesitate to ask questions during the presentation. We'll try to monitor. If you can raise your hand, is a little bit easier. And then at the end of the presentation, we also stay for questions or clarifications. Okay, so welcome again, and thank you, Professor Barnes.
Thank you very much. Can you hear me?
Yes.
Good. And last test is, can you see this?
Yes.
Beautiful. Okay, so I won't be able to see raised hands the way I'm set up. So just, Pierre, maybe you could stop me, interrupt me, whatever you need to do.
Yes, we'll do that.
All right.
We'll
Thank you. Okay, here we go. So thank you so much for the invitation. I am a climate scientist by training who now really sits at the intersection between explainable AI and earth science in general. I love thinking about both earth science problems, but also building tools to address them and make progress on hard problems. And so that is the perspective I'm going to give you today. So just big picture, a sobering thought here. Humanity as a whole, we face a very challenging future. The Earth system is threatened. Global environmental change is pushing the Earth and society well outside of our experience, as well as the environmental, state that the Earth has ever been in. On top of this, when we think about just humanity and moving about the globe, unprecedented numbers of people are being impacted and seeking to escape from worsening climate hazards, and this will not get better over the next few decades. And then finally, where I see my work fit in this big picture is that anticipating what's to come, so predicting human Earth system futures and change is going to be really critical for preparing society as we navigate this future. So AI for climate, for those of you on more the earth science side, I like to point out that we have many tools in earth science, in climate science. And machine learning is just one of them. This is not the end all be all. We still need our saw and our screwdriver and our wrench, but maybe machine learning is that extra tool in the toolbox. And it's not new. You can find examples of machine learning in climate going back many decades. In fact, this paper on the right here from 1964, applying, if you look in the bottom right, a very simple neural network setup. So this logistic regression here for meteorological prediction. So it's not new, but certainly the explosion has introduced new ideas and new tools over the last, say, 8 years or so. One of the things that makes our field so exciting to work in this space is we have so much data. Most of the data collected, especially from satellites, is never looked at or used. And so the point is where there are many systems on Earth that we do not have great data sets, don't get me wrong, but many of the tasks and problems I'm going to talk to you about today are not data limited per se, but it's how do we mine information from that data. So I'm going to talk through a few applications of how machine learning is being used in the field already, because I don't have time to talk about all of them and I don't work in all of them. But just to give you a flavor, one very well-known way of using machine learning, and honestly any statistical data-driven tools in general for decades, has been the post-processing of climate or weather or Earth system data. For example, here is a case or a set of papers predicting the errors of our current weather forecast systems. So not necessarily using machine learning to make the forecast themselves, but rather to post-process the output of our dynamical physics-based models to make them even better. Another is improving climate model parameterizations. This is when AI really hit our field in 2018 with multiple papers showing that machine learning may help us better model, especially the small scale processes in the atmosphere. In this case, one of the biggest uncertainties in climate science and climate science modeling being that of cloud processes. And so there's a lot of work being done in that space. Another one, and here's a cow, bet you didn't think you'd see a cow today in a slide, But I like to point out that a lot of Earth system problems have many downstream impacts. And so there's colleagues here at CSU thinking about dairy production on, say, a daily or weekly basis. And they know that the weather and climate conditions are important. But if you think about taking things like temperature in units of Kelvin and precipitation in units of millimeters and converting that through many steps of the causal chain to dairy production, that's really complicated. And we don't have a full set of well-known fundamental equations to understand all of the processes to get from the weather to dairy production. And in many ways, these AI and machine learning tools allow us to model these activities without knowing all of the details yet. Another case of using machine learning in our field that I think is going to be a very big step forward as we continue to explore is that of transfer learning. So I already mentioned how much data we have. Well, it's not all perfect. Actually, most of it isn't perfect at all. And much of it comes from climate model output, which I'll talk more about today. Climate models are amazing tools, but they certainly have their errors and imperfections. And so one exciting avenue is to train machine learning algorithms on climate model output, where we have hundreds of thousands of years of simulations, and then fine tune it with observations to try to get sort of the best of both worlds and ultimately do a better job predicting reality. Another big thing going on right now is the advent of deep learning weather and climate emulators. That is, models that are purely AI from the insides to the out. There's a lot of work being done in this space right now, and I actually not exaggerating, every morning I wake up to a new one coming out in archive, a new preprint. And so this is certainly an area that is growing rapidly. And we're going to see a lot more in this area. And then another point here is that AI is being used for climate change communication. That is, it's easier to visualize what the world will look like when you can maybe see some of these climate hazards in your own neighborhood. So you can go to this website, for example, and look up your address, and it will show you what your neighborhood would look like, say, on fire or in a flooded conditions. So these are using generative techniques. And then I'm a scientist, so ultimately my goal is to learn new things. And another really exciting area here is equation discovery. So using machine learning techniques to learn from data, which is something we've been doing obviously since beginning of measurement, but to learn from data to actually try to output and understand missing terms in our dynamical equations. All right, so that's a big overview. I'm going to talk more specifically about the work my group is doing here. And one of our goals is to develop and implement AI tools to leverage these imperfect climate models, so these imperfect realizations of what the world looks like, in support of Earth system prediction across time and space. And again, I want to re-emphasize climate models are inaccurate but invaluable parallel universes that we can mine for information. So we're going to start on long time scales, and throughout the talk slowly zoom into shorter and shorter time scales. So we're going to begin by thinking about climate change and global warming, and thinking about how much time do we have until critical global warming thresholds are reached. So you may have heard or read in the news things about, say, reaching 1.5 degrees or 2 degrees above pre-industrial levels. Now, these numbers themselves are not some threshold that's set in stone by the Earth system. They're not tipping points per se at all, but they are numbers that can help reflect and help explain the types of consequences that are coming if we continue on this current path. You'll see on the bottom, though, while we can talk about reaching these thresholds or when we may reach them, we don't know when. So that's the question marks on the bottom. What year might we expect to hit 1.5 or 2 degrees above those pre-industrial levels? And the reason this is so hard is our climate models all give us different projections of this timing. So here are 3 different time series. So year on the x-axis and the temperature above, so degrees above that pre-industrial level on the y. And the 3 different panels show 3 different future climate change scenarios. So the smaller numbers on the right, so SSP 126, reflecting the fact that we really get our act together, doing with reducing carbon emissions, but also take carbon dioxide removal from the atmosphere. And what's What's going on here is that while these dashed lines show these different temperature thresholds, 1.5, 2 degrees, et cetera, the different colored lines are different climate models. So different realizations of the real world. And you can see they cross those thresholds at very different times. So for example, in the leftmost panel, one model, the purple model, surpassing 2 degrees C by the early 21st century, and others like the green and the yellow model taking till about 2050. So the question is, this is a large range of uncertainty. Can we do better? So what we've done, and I want to point out there are many other ways to do this problem, and colleagues are working on them, but the way our group chose to approach this is we trained a neural network to take in maps of annual mean temperature. So everybody think of a year, maybe the year you were born, and imagine taking the annual mean temperature map from that year, in this case from climate models. We're going to make use of climate models where we have many realizations. So we're going to take a map of a year and we're going to put it through our neural network, and we're going to have the neural network predict how many years until a particular warming threshold is reached. For example, how many years until 2 degrees above pre-industrial is reached in these simulations. Now we're going to do a bit more than this. We're not just going to predict the year deterministically. We're actually going to predict, in this case, we're doing parametric predictions. So we're going to predict these 4 parameters of what we call the Shash distribution. And what it does is it allows us to get us to estimate a certain amount of uncertainty in the predictions, as well as allowing for skewness in either direction. So we make our predictions. And first, you might wonder, how does the network do? It does well on our held out testing data. So here is on the x-axis, the true number of years until the threshold is reached, and on the y is the predicted. And what you want to see is the blue testing data lying along the one-to-one, and overall it looks pretty good. All right, but no one actually probably cares when a climate model is going to reach these thresholds. They want to know when the real world will reach these thresholds. So once we've trained this network on climate model data and made sure it can do an okay job at testing, at the testing set, we can now push real world observed temperature maps through the network and have it predict how many years does the network think, in quotes, we have until 2 degrees C is reached, for example. So in this case, here are 4 example temperature maps from an observational data set. And we can ask, when does it predict we will reach 2 degrees? And we can do more than this. We can actually, for every map that we have, predict how many years until we reach 2 degrees. And that's what I'm showing you here. So on the x-axis is the year of the observed map we put into the network. And on the y-axis is how many years it says until we reach 2 degrees C. So what the network's doing is it's looking for warming patterns or fingerprints of the warming patterns due to climate change that are representative of how many years we have until we hit 2 degrees above pre-industrial. So one thing we'd like to make sure of is that our model isn't giving us just completely garbage results, because we don't actually know the right answer here. We haven't reached it yet. And so one thing we look for is that for every year we step forward and put in a new map, we should be 1 year closer to 2 degrees C in general, if the network is being consistent through time. And indeed, we see that is the case with a slope of approximately -1 years per year. So you might be looking at this and say, hold on a second, it's not always a slope of -1 year per year, which is true. For example, there's a bump here in 1991 and 2, and that's actually the eruption of Mount Pinatubo. So when Mount Pinatubo erupted, it released a bunch of aerosols in the stratosphere, which ended up cooling the Earth for multiple years after, which is a well-known phenomena. And in fact, our network does not know about volcanoes, and so it assumed that we had gone sort of back in time and we were further away from reaching 2 degrees C. Once these aerosols deposited, we were then back on track. And so in this way, I actually find this telling that the network is sort of reacting to changes into the temperature maps in a way that honestly is physical and makes sense. So we can do this under different scenario assumptions. So whether we're on climate change scenario SSP 370 or on that much, with carbon removal, et cetera, SSP 126, so that's in the blue. And we see different estimates with, again, some width of uncertainty for when we will reach these different temperature thresholds. And the big point here is, compared to other estimates, we find a higher likelihood of reaching 2 degrees C, even in this blue, in this low scenario. But I want to point out it isn't ruled out that we could avoid 2 degrees C. So that was just for the globe, but what about regionally? So we've repeated this study, but now focusing regionally on for many of the regions across the globe. In this case, focusing on Central North America, we're going to apply transfer learning. So far, all I've done is train on climate model output and then sort of cross my fingers and hope it does a good job for the real world. Instead, we're going to take the approach now of training on climate model output, but then fine tuning with the small amount of observational data that we do indeed have. So that is, we're going to fine tune on the limited observations of hitting 0.8, 1 degree, and 1.2 degrees C, which we already have, and then use those networks to predict the observations. And so this is what the result looks like. The black is the observed temperature over the Central North America over the last few decades. The blue line is what our base network predicts, is the sort of the time series of when we will hit different thresholds. And the orange is once we've performed transfer learning. And so you can see that this transfer learning approach really, this fine-tuning approach updates the network enough to fit more with the observations that we've had to date. So one of the questions you might be asking with this, at least that I asked, is how did the network update its prediction? This seems like something that we should understand and is interesting. So what if we could learn which regions of the globe were most relevant to the network predicting the observations, that this transfer learning process? And that's where explainable AI techniques come in. So this idea of opening the black box, there's been a ton of work in the computer science world, et cetera, on this in this area. And indeed, in the last 5 years or so, our field as well has started embracing explainable AI techniques for specific Earth system problems. So there are many, many explainability methods out there. I'm happy to talk about them during the Q&A, but here is one method. It's called an attribution method that I like, because it often aligns with how climate scientists pose their questions. And specifically, imagine you have a network, in this case, that predicts the probability of a cat being in an image. You input a picture of a cat and it outputs a probability of 0.8, and you want to understand, where does this 0.8 come from? Well, these methods work in a variety of ways. In this case, the method takes that 0.8 and propagates it back through the network through a series of sort of arithmetic calculations to produce a heat map showing you the most relevant regions to that 0.8 prediction. So if you see here on the heat map that's created, we see that the region there is a cat is the most important region to determining there is a cat, which is probably mostly obvious to us, but it will get more interesting when we start applying it to climate problems where we don't really know the right answer. So why use explainable AI? This is one of my favorite examples of all time. I can't take any credit for it, but this paper by Lapushkin is fantastic. One of the big reasons explainable AI is helpful is it helps you understand whether your approach is, or your network is making the right answers for the right reasons, or getting the right answers for the right reasons. So let me give you an example here from this paper. So we've trained a network to predict if there's a horse in an image. And I hope you agree there are horses in both of these images. And the network also got it right. It says, yes, there are horses in these images. Great. And then we can use explainable AI to make heat maps of the most relevant regions for the network's correct prediction. And in this case, these red blobs denote the hot spots for this attribution heat map. And if you sort of squint, you can maybe convince yourself that the red dots align somewhat with regions where there are horses. So it's just telling us it identified the horses to predict there was a horse. Let's do another set of examples, however. Here are 3 more examples of horse images. And again, the network got them all correct, said, yes, there are horses in all these images. Once again, we can apply these explainable AI attribution methods. And now the heat map looks a bit different than you might expect. So in this case, the most relevant regions are not where there are horses at all, but in the bottom left-hand corner. And you may have caught this already. I can't see anybody's face here, but it's highlighting that the network is using the copyright symbol in the bottom left-hand corner of each of these images to determine if there is a horse. And that's because this particular network was trained on data on images scraped from the web, and that most of the horse images came from the same German website. So from a science perspective, this is not appealing. We really would like to be getting the right answers for the right reasons, and we'd like it to apply out of sample. That is, if I go and take a picture of a horse, I would like to make sure the network can identify the horse, even if I don't have the copyright symbol in that left-hand corner. So with that in mind, there are multiple reasons then to care about explainable AI. Again, as a scientist, my goal is to understand why. So to me, that's enough. But I have absolutely been asked or told by an interested party saying, I don't care about why at all. So I don't care about explainable AI. I just want to get a good answer from this AI model. And even if that's all you care about, explainable AI helps you gauge trust in your network, like we just showed with the horse example, but it also helps you fine tune and optimize. So there are examples from our work where we used explainable AI attribution heat maps to determine how the network was making its decision. And if it didn't align with the physics and the causality we already knew, we were able to update our network approach to more align with scientific understanding. And then finally, explainable AI also helps us learn new science. And that's what I want to focus on mostly for the rest of this talk. So that is, we can identify signals we didn't know were there. As a caveat here, yes, our ultimate goal is to understand causality. And I want to be very clear, XAI does not give us causality. It's absolutely just relationships and correlations. However, I do think, and I have found, it is a step in the right direction towards causality. All right. And finally, in the last year, explainable AI has actually started getting a bunch of press as being really important for governments and setting different, for example, the Weather Act reauthorization of 2023, specifically calling out the importance of understanding our AI and machine learning algorithms. So back to this problem, we've trained a network on climate models and it made one prediction. And then we updated the network with observations and fine-tuned it to make a better prediction. And the question is, what did this update with the observations do to our network? And so what we can do is create heat maps, both for the blue network and for the orange network here. And we can take the difference of those heat maps to understand what changed in the algorithm's decision-making process. And we can make a map that looks like this. So these are changes in those, in this case, we're using Shapley values after transfer learning. And what this means, these are regions that the network is identifying for us where climate model biases, that means differences with observations, are most important for this prediction. We see a few signals here that are very interesting and we're continuing to explore. For example, the Southern Ocean off the coast of South Africa there is an important region that we know climate models struggle with, as well as regions over the Tibetan Plateau. So this allows us to start to visualize where climate model biases and errors may be most important for understanding reaching these thresholds. Okay, so let's start to zoom in a little bit on a slightly shorter time scales. So here's surface temperature trend, linear trends in surface temperature from 2021 to 2050, so a 30-year temperature trend. And why do I have 100 of these? Well, I have 100 because these are 100 different simulations from the same climate model. So for those of you not familiar, we can run our climate models. Most of our climate models to date are deterministic. You feed them the same values at the start, and they will give you the same answer. However, we know that there's chaos in the climate system. And so what we do is we start each of the simulations, in this case, 100 identical simulations, with just a small amount of noise added to the surface temperature field at the beginning. In this case, what I mean by small is 10 to the minus 14 Kelvin is added as noise, Gaussian noise, to the surface temperature fields before the start of the simulation. After only a few years, each of these simulations then splits off in different directions due to the chaotic nature of our climate system, producing different trends due to internal variability. However, because each of these still has CO2 rising, etc., still has global warming, we see that these 30-year temperature trends all in general are red. That is, we expect the world to get hotter over the next 30 years. The picture changes, though, if we reduce our trend time period from 30 years to only 10. So these are the same simulations, but now looking at linear temperature trends over the next 10 years from 2021 to 2030. What makes each of these so different is not the underlying climate change signal, which is constant throughout all of them, but rather this internal noise, or what we call natural variability of the climate system, that can confound our knowledge of what the near future holds. For example, we could be living in a world where the Southwest US actually cools over the next 10 years or warms, depending on this natural variability in its state. It might be easier to look at this in a time series. So imagine we take a single point, in this case, this is over Chicago, for 100 different realizations of a climate model simulation, each gray line denoting a different simulation. And we see once again that while there's quite a bit of noise and wiggles throughout this, we still see overall this consistent rising of temperatures. And this is what we call the forced response to climate change. However, if you focus on any individual member, so here's member number 40, you start to see the ups and downs, the swings of temperature over this location due to this natural climate variability. And if you chose a different member, you would get a different picture of the ups and downs due to natural climate variability. And so one of the questions my group works on is to what, first of all, and as I've just shown you in the first example, is thinking about these global warming projections and trying to fuse simulations and observations together to get a better approximation of this trend. But also, we're interested in what we call multi-year predictability. That is, can we predict these ups and downs due to natural variability that sit and reside on top of this longer-term warming? Now, predicting things over the next few decades is important, not just to prepare for weather and climate hazards, but also to anticipate the masking of the intended effects of climate policies. For example, you could imagine if the world got its act together and actually started doing a lot of hard work with carbon emissions, and then the next 10 years were then hotter than ever, there could be some issues from more of a public perception of whether or not what they were doing was working. And so being able to anticipate this natural variability could end up being very important to see climate policies succeed. And then even on the shorter timescales, my group works on predictability on weekly timescales. So can we predict what's going to happen in the next, say, 2, 3, 4, 5 weeks from now? So beyond the weather timescale. But maybe this is, well, this is probably obvious to everyone. Climate prediction is really challenging, and we cannot expect to make perfect predictions all of the time. And this is one of the things I find fascinating about Earth system applications of AI compared to many of the commercial applications. In our area, my goal is never to get a perfect prediction because I just know that won't ever happen. Instead, it's how do I identify the predictable signals when they are there? And so we call this looking for specific states of the Earth system that lead to enhanced predictable behavior, forecasts of opportunity, or sometimes we call this state-dependent predictability. And this is really, in my view, one of the places that AI can really help us is identifying these periods. So in a very simple XY plot, I sometimes think of the climate system as 80% of the system is just noise that's going to be hard to predict. But what I'm looking for is that 20% of signal, 20% of that line there where all my data lines up. And one of the questions is impossible predictions hampering AI learning of predictable behavior? And this is one of those questions that we continue to explore neural network architectures that may help us in this area. So where does this 20% of the data, the signal, come from? There are multiple phenomena. You may be familiar with the El Nino Southern Oscillation, which operates on about 2-year timescales and can lend predictability across the globe. And also something called the Madden-Julian Oscillation, which is a semi-periodic wave that propagates from the west to the east along the equator on timescales of about 20 to 90 or so days. And in doing so, this can lead to predictable behavior in the northern and southern mid-latitudes. So let me give you an example of how we use this forecast of opportunity and how we can pull it out with a neural network. So here's some work where we're trying to predict ocean temperatures over the next 5 years. And so what we do into our neural network is we input past sea surface temperatures, and we predict whether the temperatures over the ocean are going to be warmer than normal, average, so neutral, or cooler than normal over the next 5 years. And we do this for every grid point over the globe, over the ocean. And if you look at the accuracy of this approach, so this is where we've trained with a climate model and tested on the same climate model, just on data, withheld data. So that is, we are training on 3,630 years of data, something we certainly don't have in observations. And then we are evaluating on the same model. The way we've set up the problem, random chance is 33%, which is about that light yellow color. And you can see from the overall accuracy, it looks like we're doing about a little bit better than random chance, which is why this is a hard problem. However, if we only focus on the samples where the network is confident in its prediction, and I haven't talked about how we do that, but we do that in a variety of ways with uncertainty quantification and looking when the network thinks the uncertainty is smaller or narrower, we start to see that the accuracy improves when we focus on the predictable signals identified by the network. And furthermore, if we look at the 20% most confident predictions, we find there is indeed skillful predictability across the globe in certain regions. Well, this is just a climate model, though, predicting a climate model, which again is not the goal. We want to predict observations. So what Frances Davenport, the lead author of this project, did is she then took this neural network and applied it to observed sea surface temperature predictions. And you'll see we get a similar story. If one had not taken the state-dependent predictability approach, that is the far left plot, they would have thought the network's not much better than random chance. But if you again focus on state-dependent predictability identified by the network, we do see predictable behavior, especially in the North Atlantic, which is known to be a region of the globe with predictability at certain times. So returning now to explainable AI, we can now ask the question, where is this predictability coming from? Can we identify the sources of predictability that the network is using? And the answer is yes. So similar setup here, using a neural network to ingest sea surface temperatures and predict, in this case, the temperature over land in the coming 5 years. We make these predictions, we train the network on climate model output, we make these predictions, and then we use explainable AI to identify these sources of predictability. And in doing so, we can make these heat maps. In this case, these are 4 different heat maps for 4 different predictions across the globe. And we see that the network's identifying different regions of the ocean lending predictability. So for example, if you want to understand Midwest temperatures over the US, so the bottom left, it's really identifying the El Nino Southern Oscillation, or ENSO. Whereas the case for Mexico, it's identifying what's called the Kuroshio extension as a source of predictability on these 5-year timescales. This is for different locations or different prediction locations, but even for the same location, so in this case, predicting temperatures along the west coast of the United States, the network, because of its nonlinear behavior and its finding remote relationships across the data, it can identify different sources of predictability depending on the when, so when this prediction is being made. So once again, we see patterns associated with well-known climate modes, both over the North Atlantic and in the North Pacific, the Eastern North Pacific, as well as, once again, that Kuroshio extension coming off of Japan. And now we can use these to better understand these sources and the processes leading to predictable behavior of surface temperature on these 5-year timescales. So we're going to zoom in even further now and say, well, that was multi-year prediction. What about shorter term prediction? So we call this sub-seasonal to seasonal prediction. And it can be very important for reservoir managers as an example application in monitoring whether they're expecting more rain and whether they should let water out of their reservoirs or retain it in case they are entering a drought. So we've done quite a bit of work on this, but I'm only going to briefly show you some examples of how we can use explainable AI to explore this problem. Specifically, here we take neural networks to take in information from the tropics. So this represents things like that Madden-Julian oscillation or the El Nino Southern Oscillation. So those different modes, climate modes that may lend predictability to predict. Oh, yep.
Elizabeth, yeah, sorry, just a question for John Giacomo.
Yep.
I guess I can read it or you can read it. So he's wondering, when you say layer-wise relevance propagation, what type of LRP did you use for the heat map? Was
Yeah,
it
so yeah. So in that case, that was alpha equals 1, beta equals 0. There are a bunch of LRP methods. I'm now typically, I have half of my plots, I use deep SHAP as well. So LRP was just one example of heat maps that we use for attribution. There's also LRP-Z that I've used as well.
got it. Thank you. Is
Great.
that fine, John Giacomo? Okay, thank you. Yeah, he said thank you.
Yep. And I'm happy to
Yes,
talk
it
about
is.
that at the end too. Yep. So
Thank you.
we're training a neural network to, again, try to identify sources of predictability of the jet stream, so the atmospheric circulation over the Pacific in the coming 3 weeks. Now, I could show you lots of plots on this, but to keep it simple, one of the interesting things we can do is train neural networks to make these sub-seasonal predictions using climate model data, but we can use climate model data of a historical climate as well as of a future under climate change, so say in 2100. And when we look at the predictability in these two different worlds, we can start to assess the extent to which climate change impacts the predictable signals on sub-seasonal predictability. So once again, if we looked at all predictions, so that's the far left of this plot, our accuracy is very similar between the two simulations. But as we look at the more and more confident predictions, so moving right on this plot, we see that in the future, under climate change, these forecasts of opportunity decrease in skill. And then we can use explainable AI to ask why, what changed between the historical period and the future period. And we can make these heat maps to identify the fact, in this case, that changes in ENSO dynamics are actually what are leading to changes and decreases in forecast skill in the future. All right, so zooming out now, we've done some other work, not just on the climate system itself, but also starting to think about the coupling between the society, human development, and the Earth system and extremes. So one question we're asking is thinking about human development and environmental factors and how they are connected. And so one of the papers we wrote back in 2021 was trying to predict the human footprint, which is an index largely used by the ecological community. And it's a number between, give or take, a scaled number between 0 and 1, where 0 means the landscape is untouched, and 1 means that you can think of it as a parking lot of a mall. And they use this data set extensively to do a lot of work and studies. However, it takes a long time to create. So what we do is we leverage this data set that was already created by this community, in this case, Williams et al. 2020, and we attempt to learn this index from Landsat imagery alone. That is, we take in imagery from Landsat over a certain set of pixels, and we predict this human footprint index. Well, we can do this for the year 2000 when the human footprint index already exists, but then once we have a network that can perform this calculation, we can make predictions of the human footprint index across the globe for any year where we have Landsat imagery, in which case we have a lot of it. So we've done this work, and it, to be honest, worked surprisingly well. And what we're doing now, oh yeah, before I tell you what we're doing now, one second. This is one of the cases where we used explainable AI quite a bit to ensure we were getting the right answers for the right reasons. So on the left here, this is one of my favorite cases in Sumatra. On the left is the year 2000 Landsat imagery. In the middle is the 2019 imagery. And on the right is the explainability heat map telling us and explaining the network's decision-making or the most relevant regions for the decision-making process of why the human footprint doubled between 2000 and 2019. And what we see, one of the main regions is this highway, and it turns out this is the Trans-Sumatran Highway that went in 2019, and the network has identified this as important for why the human footprint index has gone up, giving us some, I guess, building trust in our network's predictions. It also, XAI helped us determine which Landsat channels were potentially most important for the network's decisions. Once again, showing that we can both use XAI both for gauging trust and fine-tuning and optimizing our algorithms. So we did this for many different locations. and many different changes, and found lots of, it was really fun. One example that was particularly interesting is in the bottom right-hand corner. This was a region that our neural network identified as having a high human footprint index, but our label, our truth, did not. And it turns out it was an illegal gold mine, artisanal gold mine, in this region of Indonesia that our network was able to pick out from the satellite imagery. And right now, what does this have to do with, climate? We are starting to develop a global yearly index, so one can start to begin to look at time series and the impacts of, for example, tropical cyclones and hurricanes, and how they impact human development across the globe. All right, so in my final few minutes here, I've told you all about how we're using explainable AI to try and learn sources of predictability and identify these interactions between humans and the climate system. But I do want to point out explainable AI has its own problems. And there's some really great papers. This is one of my favorite. It's pretty old now, from Rudin 2019, saying we need to stop explaining black box models and instead use interpretable models. And in this case, what I mean by interpretable AI is algorithms that explicitly incorporate the decision-making process into its structure. So they're interpretable by design, by the designer, by the human that made it. Because we need more than just explainable AI identifying where the network is looking, but we need to also understand how it is using that information, which is still very difficult to do. So our goal in the group is to work towards building interpretable AI models that mimic our climate scientific human reasoning to improve that intrinsic interpretability. This is a slow process. It is a lot of fun though, but it takes time. It's a lot harder than just training a black box model. And one of the ways we have approached this, amongst others, is taking cues from the extensive work done in the computer science community. In this case, in this paper, it's called This Looks Like That. And they build an interpretable network for bird identification by saying, we're going to find prototypical images in the training set that help us identify the bird type. So in this case, saying this head of this new test image bird looks like this head that I saw before in the training set. And so slowly adding up points between how much each part of an image looks like a learned prototype to ultimately predict or classify the bird. So the way many of these methods work is from computer science is that this looks like that anywhere. It doesn't matter if the bird is upside down or on its side. A head of a bird is a head of a bird. But in Earth science, location matters, right? It's not about relative location. It matters if something is in the Pacific Ocean, it's very different and has very different impacts than if it's over the Atlantic. And so because of that, we're starting to design approaches that we call This Looks Like That There, being very specific to the location. And so this is work by former master student Nico Gordillo, identifying prototypes in the tropical Pacific Ocean that serve as sources of predictability for mid-latitude weather. We're furthermore extending this to take cues from something called analog forecasting that has its roots back from the 60s from Ed Lorenz and others, and using analog forecasting that is identifying states in the past, or in our case, states in climate models that look a lot like today, and making the assumption that they will evolve similarly into the future. But we're using machine learning, so interpretable AI, to help identify masks or weightings for identifying these analogs. And for those of you familiar, you can think of this as a form of soft attention. So allowing us to focus our attention on certain regions of the globe, most important for identifying the best analogs for prediction. So in my view, these are really exciting times. I'm having so much fun getting to work at this intersection, and there's a lot more going on in the field than what I've told you about today. For example, generative AI for downscaling, for making huge ensembles, and for what we call data assimilation. So ingesting in situ observations within our models to make better predictions are going to be huge areas for growth in the next year or two. Another big unknown is the extent to which and how much climate change will influence the performance of our AI models. So many of them to date are being trained over data from the last 40 to 60 years, where we've seen large changes in the climate. So it certainly hasn't been stationary, and we expect those changes to continue forward. So to what extent do the AI models trained today, will they be applicable and useful in the coming years? And then I've already mentioned this idea of emulators, or sometimes you can hear the phrase digital twin. I don't like that phrase, but it's out there, for weather, and so AI emulators of weather and climate for full model replacement. We are seeing a lot of innovation right now. A big area, especially for climate, is the extent to which we can start to couple the ocean and the atmosphere together. So can we have an AI model representing not just the atmosphere, but the ocean and potentially the biosphere as we move forward. So with that, thank you for listening. And I believe I have about 10 minutes for questions.
Yeah, thank you very much, Elizabeth. A great and inspiring presentation. So thank you also, everyone. Anybody has any questions? Maybe to make it easier, if you can raise your hand, and then so that we don't start asking questions all at the same time. Yeah. Yeah, go ahead, Mohammed. You can say something.
Oh, okay. I was wondering if you have an example where AI was able to make a breakthrough in explaining the teleconnections, the dynamics of the teleconnections that you have shown, or presenting a surprising results that we didn't know before.
Yeah, so I think, if you were to just, I'm going to answer the question in a minute, but I'm first going to reword it slightly. If you were to replace AI with any method, I would actually say that is also a tricky question, because at least in our field, it's called the quiet revolution of weather forecasting. There's a great example paper out there of the fact that we've been making incremental changes. And so I don't see AI as coming in and completely transforming everything, because we actually know a lot already about the weather and climate system. So I don't expect it to suddenly be a step change. With that said, I'm now going to answer the actual question that you asked me. One area that has made a big difference, I think, is in this concept of forecasts of opportunity. Because up until now, our methods for looking for these were all linear, which meant that they just had to sort of be the same pattern that was stronger or weaker and coming in and out. And if you look back at the climate literature, that's really how we've approached the problem to date. And I do think that what has been surprising to us and to others is that there is skill in there that you can identify before you make, when you make the forecast, which is important. It's not retrospective, in which case that's cheating. But that there actually is skill there, and the ability to transfer from climate model space to observational space was incredibly complicated due to these climate model biases. So I think, in my view, those are two areas scientifically where we're making progress. If we're going to really look at the big step change, I think the other one if there is one, I think the one we're going to see is if these emulators can get good enough and on par with what we think we need, the ability to simulate large ensembles. And by the large, I mean thousands of members for uncertainty quantification. Right now, our largest weather ensemble is 50 members out of, say, ECMWF. And now we could be doing 5,000 or 50,000 in the same computing, with the same computing. So I think that is going to be a big area if we see that, if we see this step change. Yeah.
Thank you.
Yeah, thank you, Mohammed. So we have two questions from the chat. So one, I'm sure you can read them, Elizabeth, but maybe I can read them. So first one from Luisa Gianluca. So it's two questions. So do you see any difference in the models for the atmosphere versus ocean? And is one of them easier to predict? And then she also mentioned how do you see the combination of the modeling and human development and the impact in climate change? And then VJ will do your questions next.
Okay. Yeah, so I'm not sure if your model, if model means AI models, or if it means our climate models, or it just means our understanding models. We need more words. But I will say one of the tricks, so which is easier? I think they are both incredibly challenging. One thing that makes the ocean even harder, however, is the lack of observations in comparison to the atmosphere. Also, the longer time scales. So when we talk about training AI models or AI emulators for the atmosphere and ocean, I don't know how we'd compare apples to, you know, to pies here, but I think the ocean will ultimately be more challenging because the longer timescales require longer records of OBS, which we don't have, and it's just that much harder to sample the ocean. And there's still a lot of the fundamental dynamics of the ocean that we really don't understand in a way that we've known about the atmosphere for many years. So because of that, if I had to give an answer, I'd say the ocean is by far harder. And then this combination of modeling heat development and the impact of climate change. So one of the things we are looking for in this, starting to merge this information, is many of us climate scientists often think of our applications and of temperature, you know, on the grid box by grid box scale. And this human development index is really allowing us to put it into a context of where people, not just are by population, but where humans are using and interacting with that land. And so in that sense, it's almost just a reshaping of the bounds within which we are doing our work. Many others use it for far more than that. For example, we did work and have others with sustainable development goals. So there's lots of other applications. I merely wanted to point out just one here for that human development index. Okay, and then there was another question. Yeah.
Yeah, another one from VJ. I mean, I'll read it for everyone. So great presentation. So basically, you're using building tools tailored to climate science. There are many methods out there. Why would you choose specific method? Also, have you thought about scientific machine learning or PINs?
Yeah, so there are many methods out there. Why would you use a specific method? I mean, my short answer is because I'm not aware of every method out there. And so the ones I'm aware of, I could potentially use. Another thing that I do think a lot about is simplicity, that ultimately the methods I choose to use, I choose them because I need them to be complex enough to do the job, but they don't have to be more complex than necessary. And also my goal is for my community to read our papers and be inspired to use those methods as well. And the more complex, the harder it is for buy-in, especially from those that are still dragging their feet on AI in the first place. And so that is one way that we choose those methods. It's also impossible to keep up with the state of the art. And so I'm no longer trying. I'm trying to identify the tools I think will be most beneficial, not necessarily the shiniest new toy, of which there are many exciting ones that I mean, I wish we could work that fast. Also, in terms of scientific machine learning or physics informed, this is a big area people ask us about. So some applications already in the field are in parameterization. So understanding, say, cloud processes within our climate models. Already, those are statistical relationships that have been derived from a few data points. And we're using machine learning to try to get slightly better statistical relationships. And in those cases, including physical constraints like mass conservation is one, actually is very straightforward. On the scales I'm working at, where there aren't as simple of F equals MA that we just built into our neural network. The second you start going down that direction, you're really building a dynamical model in the first place. But instead, the way I would argue we are already doing physics informed machine learning in how we set up our problems, in the way we frame the task, in how we set up that interpretable piece and why we do it that way. The forecast of opportunity perspective is coming from our physical knowledge of the climate system and how it works. So in that sense, I tend to take a much broader view of what a pin actually is. But yeah, great. And I know it's the top of the hour, so.
That's fine. There's still at least one more question. We have stayed a little bit later. Pierre is not in my family. At least there's a few of them. The time is not something they pay too much attention to. So, but at least that question from Dan. So do you evaluate the stability of the XI methods, especially post-processing ones? And you explain the model after it is trained. After all, AI models have inherent stochasticity.
Yeah, so we actually have quite a few papers on like the good, the bad, the ugly on XAI for climate science applications as well. So absolutely. So a few things. First of all, there's the AI model themselves that have stochasticity. So we will train many models, and the hope being that if we get consistent answers, that it may be more than noise. Also, the XAI method themselves, they all are ultimately fitting approximations to the actual neural network that we have trained. And this is one argument away from XAI and towards more interpretable approaches. We also tend to apply multiple XAI methods to the same problem in our papers to ensure, once again, that we don't end up with a completely different interpretation of the network's decision-making process. So in that sense, it's not one pathway to getting the answer. It's really trying many, which is pretty common in our field anyway. We rarely will run one simulation of anything and call it good, again, because of that stochasticity or chaotic nature. So it seems to be pretty standard for just my community to go through and try lots of different things and make sure they generally agree.
Thank you. Ananta is the hand raised up. Go ahead.
Thank you for the great talk. I had one question. So, for your predictions on the 2D field, do you use something like a CNN, or have you used more globalized networks, I guess, like transformers? The reason I'm asking is in a CNN, you kind of assume a uniform, equi-spaced grid, right? So that might lead to some errors far away from the equator, maybe near the poles. Have you observed something like that in your work?
Yeah, so us personally, we've used even dense networks are fine for some of our applications because I think what we're finding are pretty large scale simple patterns once they're identified. We've used CNNs, and yes, you're right, the grid can be an issue. It has not been an issue for the applications we've shown, but it has been certainly an issue for others, especially say these pure AI weather models. A lot of thought has to go into what grid do they project the data onto in order to have this done well. There's a long history in our field of actually our physics-based dynamical models doing things in spectral space. And so we're starting to see AI models go back, sort of backwards in time to both spherical and spectral, 2D spectral space. And that has shown some improvement. So the answer is yes. It's not always critical. And in my applications, I don't think it would make any difference really, but there are many applications where that is important. And yes, there are lots of groups thinking about transformers, again, an attention-based approach for some of these problems. And those are promising, as are other methods. So I think right now we're sort of getting the buffet and nobody knows what to put on their plate. Yeah.
Thank you.
Okay, thank you. Any other last burning questions? Okay, so it's the last call for questions. So if there's no more question, thank you very much, Elizabeth, and for a great presentation. I think we only have amazing replies and comments, but thank you also for the attendance. It's always a pleasure to see you here. And if you did like the presentation, remember we try to organize those every month. So we also have community meetings where you can come and talk to different experts in the field or less experts. And so make sure to spread the word around, and we hope we'll see you again.